Welcome everyone to our exploration of work, energy, and power, three crucial concepts that govern motion and energy transformation in our world. We'll dive into the definitions, applications, and interconnections of these fundamental principles, shedding light on how they shape our understanding of the physical universe. This opening slide sets the stage for our journey, highlighting the importance of mastering these topics to gain a deeper appreciation for the forces that drive the motion and change we observe all around us. As we progress through the presentation, we'll unpack each concept in detail, examining real-world examples and the mathematical relationships that describe them. By the end, you'll have a comprehensive understanding of how work, energy, and power work together to explain the mechanics of our dynamic world. Work is the transfer of energy that occurs when a force is applied to an object, causing it to move a certain distance. This is a fundamental concept in physics that helps us understand how forces interact with objects and how energy is transformed. We encounter work in many everyday activities, like lifting a bag of groceries or pushing a car. In these cases, we exert a force that causes an object to move, resulting in work being done. The amount of work performed depends on the force applied and the distance the object moves. Understanding the concept of work is crucial for analyzing how energy is used and transformed in various physical processes and everyday tasks. The key formula for calculating work is work, W, equals force, F, x distance, D. This represents the amount of work done by applying a force over a certain distance. Let's look at an example. Pushing a shopping cart uphill. The work you do is equal to the force you apply to move the cart, multiplied by the distance you push it. The formula provides a simple way to quantify the work required to move an object a given distance by applying a force. Understanding this basic formula is crucial for analyzing physical systems and processes that involve the transfer of energy through work. The standard unit of work in the International System of Units, SI, is the joule, J. 1 joule is defined as the amount of work done when a force of 1 Newton, N, is applied over a distance of 1 meter, M. Work is a scalar quantity, meaning it only has magnitude and no direction. While the joule is the most common unit, other units like the erg in the CGS system and the foot-pound in engineering are also used depending on the context. Positive work occurs when the force and displacement are in the same direction, helping the object move as desired. For example, lifting a weight vertically applies an upward force and the weight moves upward. This is positive work. Negative work happens when the force opposes the object's displacement, hindering its motion. Pushing a box across a floor, where friction acts against the box's movement, is an example of negative work. The key distinction is the relationship between the force and the object's displacement, positive when aligned, negative when opposing. Force is a push or pull that can change an object's motion. It can start, stop, or change the direction or speed of an object. Work is done when a force causes an object to move over a certain distance. In other words, work happens when there's movement caused by a force. The image shows a person pushing a heavy box across a smooth floor, demonstrating the concepts of force and work. The warm lighting and sense of effort and accomplishment in the warehouse setting help visualize these physics principles in action. Energy is the fundamental ability to do work and drive change in the world around us. It comes in many different forms, from the energy that powers our bodies to the energy that lights our homes. Energy is what enables motion, transformation, and interaction. It is the driving force behind all natural phenomena and our technological advancements. Understanding the nature of energy is crucial, as it underpins our entire physical universe and everything we do. Kinetic energy is the energy of motion. Any object that is moving has kinetic energy, and the faster it moves, the more kinetic energy it has. Examples of things with kinetic energy: a speeding car, a running child, a spinning top. Potential energy is stored energy an object has due to its position or state. Examples of things with potential energy: a book held above the ground, a stretched rubber band, a compressed spring. Thermal energy is the energy associated with the random motion of atoms and molecules in a substance. The more thermal energy a substance has, the hotter it is. Examples of things with thermal energy: a boiling pot of water, a hot stove burner, a burning fire. Chemical energy is the energy stored in the bonds between atoms and molecules. When these bonds are broken, energy is released. Examples of things with chemical energy: food, batteries, fuels. Kinetic energy is the energy an object has due to its motion. The faster it moves, the more kinetic energy it has. A speeding car is a great example. It has a lot of kinetic energy because it's moving at a high velocity. Two key factors determine an object's kinetic energy: mass and velocity. The more massive an object is, the more kinetic energy it has at a given velocity. Similarly, the faster an object moves, the more kinetic energy it possesses. Understanding kinetic energy is important for topics like physics, engineering, and transportation. Potential energy is stored energy that an object has due to its position or state. It's like a coiled spring ready to uncoil, or a rock on a cliff ready to fall. There are different types of potential energy. Gravitational potential energy. An object held above the ground has this due to its position in Earth's gravity. The higher it is, the more potential energy it has. Elastic potential energy. A stretched rubber band or compressed spring stores this energy due to its deformed state. When released, it converts to kinetic energy and causes the object to move. Chemical potential energy. The bonds between atoms and molecules in fuels and food store this energy. It's released when the bonds are broken, like when burning wood or digesting food. These different forms of potential energy can be converted into other forms of energy, like kinetic energy, when the object is released or the bonds are broken. Gravitational potential energy is the energy an object has due to its position in a gravitational field. The higher an object is, the more potential energy it has. More massive objects have more gravitational potential energy at the same height. The strength of gravity also affects potential energy. Less on the moon, more on Earth. Understanding gravitational potential energy is key for topics like potential energy, work, and energy transformations. Elastic potential energy is the energy stored in an object when it is stretched or compressed. This energy is stored in the bonds between the molecules of the object, which are deformed by the stretching or compression. The more an object is stretched or compressed, the more potential energy it stores. Examples of objects that store elastic potential energy include stretched rubber bands and compressed springs. Elastic potential energy is different from gravitational potential energy, which is based on an object's position in a gravitational field. Elastic potential energy depends on the stiffness of the object and the amount of stretching or compression, while gravitational potential energy depends on factors like mass and height. The flow of energy is a fundamental concept in physics, where energy can be transformed from one form to another. In this slide, we'll explore 4 key transformations between different energy forms. First, we'll see how potential energy can be converted into kinetic energy, as demonstrated by a ball falling from a height. Next, we'll discuss how kinetic energy can be transformed into thermal energy when objects collide, as you can feel when rubbing your hands together. We'll then look at how thermal energy can be converted into light energy, as illustrated by a light bulb. Finally, we'll see how chemical energy stored in fuels can be transformed into kinetic energy, powering the motion of a car. These examples highlight the versatility and interconnectedness of different energy forms and how they can be transformed to perform useful work. The law of conservation of energy is a fundamental principle in physics. It states that energy can neither be created nor destroyed, only transformed from one form to another. This means the total amount of energy in an isolated system remains constant over time. We don't gain or lose energy, we just see it change forms. When we observe energy changes like a falling ball or a light bulb, the energy isn't being created or destroyed. It's simply being converted from one type to another. For example, gravitational potential to kinetic, or electrical to light and heat. The key point is that the total energy involved remains the same. It just changes shape. This is a foundational concept in understanding how energy works in the physical world. Energy is the ability to do work, and it can take many different forms like kinetic, potential, and thermal energy. Power is the rate at which energy is transferred or used. It's a measure of how quickly energy is being transformed or consumed. The key relationship between energy and power is that power is the amount of work done per unit of time. So energy describes an object's capacity to perform a task, while power tells us how quickly that energy is being used. Understanding both energy and power is crucial for many applications, from engineering to everyday life. Power is the rate at which energy is transferred or used. It tells us how quickly energy is being converted from one form to another or how quickly energy is being consumed. It's a measure of how efficiently something is using or transforming energy. Power can also be defined as the amount of work done per unit of time. If you do a lot of work in a short amount of time, you have a high power output. If you do a small amount of work over a long time, you have a low power output. Instantaneous power is the power at a specific moment in time, as opposed to average power over a period. It's directly related to an object's velocity. The faster the object moves, the higher its instantaneous power. Instantaneous power is also influenced by the force acting on the object. A larger force results in higher instantaneous power. Fundamentally, instantaneous power is the rate at which energy is being transferred or used at a specific moment. The rapid spinning clock on the slide visually represents the instantaneous nature of power and how it can change rapidly over time. Average power is the overall rate at which energy is transferred or used over a specific time interval. It provides a broader picture of how energy is utilized over a period of time, rather than just looking at instantaneous power. The example of a car accelerating illustrates this. The engine's power output may fluctuate, but average power represents the total energy transferred divided by the time it took to accelerate. Average power gives us the overall rate of energy transfer, rather than just looking at momentary power values. The Watt, W, is the standard unit of power in the International System of Units, SI. 1 Watt is defined as the rate at which 1 joule, J, of energy is transferred or used in 1 second, S. While the watt is the most common unit, other units are also used depending on the context. The horsepower, HP, is often used in engineering to measure the power output of engines. 1 horsepower is approximately equal to 746 watts. The kilowatt, kW, is a larger unit of power, equal to 1,000 watts, often used to measure electrical power consumption. Power is the rate at which work is done. It measures how quickly energy is transferred or used. A high power output indicates that a large amount of work is being done in a short time. Work is the energy transferred when a force is applied to an object, causing it to move a certain distance. Work is a measure of the total energy involved in moving an object. Power is the rate at which energy is transferred or used. It measures how quickly energy is being transformed or consumed, often described as the amount of work done per unit of time. Kinetic energy is the energy an object possesses due to its motion. The faster an object moves, the more kinetic energy it has. As a car accelerates, it's gaining kinetic energy as it speeds up, and the rate at which it gains that energy is related to the power output of its engine. So power and kinetic energy are closely linked. Power determines the rate at which an object gains or loses kinetic energy. Power is the rate at which energy is transferred or used when lifting an object against gravity. When we lift an object quickly, we are using a lot of power to increase its gravitational potential energy. Gravitational potential energy is the stored energy an object has due to its position in a gravitational field. The higher we lift an object, the more gravitational potential energy it has. The rate at which we increase an object's gravitational potential energy is directly related to the power we are using. This slide introduces the topic of power and springs and how they relate to the energy of stretch and release. It discusses power and compression. When you compress a spring, you're doing work on it and transferring energy. The rate at which you do this work is the power you're applying. Stiffer springs require more power to compress them. It also discusses power and release. When a compressed spring is released, the stored potential energy is converted to kinetic energy, causing the spring to expand. The rate at which this energy is released is a measure of power. Stiffer springs will release their potential energy faster, resulting in higher power output. The key points are the relationship between power, compression, and release when it comes to springs and the energy they store and release. Efficiency is a measure of how effectively energy is transformed or used. It's the ratio of useful energy output to total energy input. Higher efficiency means a larger proportion of input energy is converted into useful output. For example, A machine that uses 100 joules of energy to produce 75 joules of useful work has 75% efficiency. Inefficiency occurs when a significant portion of input energy is lost as waste energy like heat, sound, or light. Inefficiency reduces the overall effectiveness of energy systems and can be costly. For example, traditional incandescent light bulbs are very inefficient, converting only a small fraction of electrical energy into visible light. Efficiency is a measure of how well a system converts input energy into useful output. We can calculate efficiency using the formula efficiency equals useful energy output / total energy input, x 100%. This tells us the percentage of input energy that is converted into useful work. For example, if a machine uses 100 joules of energy and produces 80 joules of useful work, its efficiency is 80%. The remaining 20% of the energy is lost as waste, like heat or sound. Efficient systems like bicycles minimize energy losses and convert most of the input energy into forward motion. Inefficient systems like incandescent bulbs waste a lot of the input energy as heat, with only a small fraction converted into light. Understanding efficiency is important for designing and evaluating the performance of various technologies and systems. The concept of 100% efficiency is a theoretical ideal, but it's not achievable in the real world. Every real-world process involves some degree of energy loss, whether it's from friction, heat generation, or sound production. Even the most carefully engineered machines and systems can't achieve perfect energy conversion. While the theoretical ideal of 100% efficiency is a useful benchmark, it's important to understand the practical limitations and energy losses that occur in actual systems and processes. The concepts of work, energy, and power are essential for understanding how we move and manipulate objects against gravity, from construction cranes lifting heavy beams to simple acts like lifting a grocery bag. The amount of work done in lifting an object is directly proportional to its weight and the height to which it's lifted. The power required to lift an object quickly is greater than the power required to lift it slowly. Power is crucial for accelerating objects, whether it's a car speeding up or a rocket launching into space. The more powerful the force applied, the faster the object accelerates. Work done in accelerating an object is equal to the change in its kinetic energy. The relationship between work, energy, and power allows us to precisely control the motion of objects, from everyday activities to complex engineering feats. Lifting an object requires doing work against the force of gravity. The amount of work done is directly proportional to the object's weight and the height it's lifted to. As you lift the object, you're transferring energy to it in the form of gravitational potential energy. The higher the object is lifted, the more gravitational potential energy it possesses. When the object is released, this stored potential energy is converted into kinetic energy as it falls. Power is directly related to the acceleration of an object. The more power applied, the faster the object accelerates. This is because power is the rate at which energy is transferred, and acceleration requires an increase in kinetic energy. When a car accelerates, its engine exerts power to overcome friction and increase the car's velocity. The power output of the engine determines how quickly the car can gain speed. A more powerful engine can accelerate the car more rapidly than a less powerful engine. The relationship between power and acceleration is a key concept to understand when analyzing the motion of objects. The key concepts we'll cover in this slide are work, energy, and power as they relate to springs and oscillations. Work is done on a spring when it's compressed or stretched, and this work is stored as potential energy in the spring's deformed state. The amount of work depends on the spring's stiffness and the extent of deformation. Energy is constantly exchanged between potential and kinetic forms as the spring oscillates. When compressed/stretched, the spring stores potential energy, which gets converted to kinetic energy as it returns to equilibrium. Power is the rate of energy transfer or use. It's highest when the spring is moving fastest, as potential energy is rapidly converted to kinetic energy, and vice versa. So the power output fluctuates throughout each oscillation cycle. Let's use roller coasters as an analogy. At the top of the first hill, the roller coaster car has maximum gravitational potential energy due to its height. This stored potential energy is like a coiled spring, ready to be released as the car descends. As the car goes down the hill, the potential energy is converted into kinetic energy, the energy of motion. The car gains speed as it races along the track. When the car climbs the next hill, the kinetic energy is gradually transformed back into potential energy, slowing the car down as it gains altitude. This continuous exchange between potential and kinetic energy is what drives the thrilling roller coaster experience. Bicycles are a great example of how we can transform energy into motion. When we pedal a bicycle, we're applying a force to the pedals, causing them to rotate and turn the chain. This force is then transferred through the drivetrain to the rear wheel, propelling the bicycle forward. The amount of work we do depends on the force we apply and the distance we pedal. For example, pedaling uphill requires more work than riding on a flat surface. As we pedal, our body's chemical energy is transformed into mechanical energy, which is then converted into the kinetic energy of the moving bicycle. However, not all of this energy is used efficiently. Some is lost due to friction in the drivetrain and between the tires and the road, dissipating as heat. The overall efficiency of a bicycle depends on factors like the quality of its components, the rider's strength, and the terrain. The internal combustion engine is a powerhouse that transforms energy in a remarkable way. The engine converts the chemical energy stored in fuel into thermal energy through combustion. This thermal energy is then transformed into mechanical energy, which is used to propel the vehicle. The work done by the expanding gases in the combustion chamber pushes the piston down, and this motion is converted into rotational motion by the crankshaft. The amount of work done is directly proportional to the amount of fuel burned and the pressure created by the combustion. The efficiency of this energy conversion process varies depending on the engine design and operating conditions. The engine's power output is determined by factors like displacement, fuel-air mixture, and combustion efficiency. Power represents how quickly the engine can do work and is expressed in units like horsepower or kilowatts. Electric motors are devices that convert electrical energy into mechanical energy, allowing us to power a wide range of devices and machinery. This conversion occurs through the interaction of magnetic fields created by an electromagnet and a permanent magnet within the motor. As electricity flows through the electromagnet, it creates a magnetic field that interacts with the field of the permanent magnet, causing the motor's shaft to rotate. The power output of an electric motor depends on factors like the voltage applied, the current flowing through the motor, and the motor's efficiency. Modern electric motors can achieve very high efficiencies, often exceeding 90%, making them highly efficient energy converters. The mechanical energy produced by the rotating shaft can then be used to power various applications, from household appliances to industrial machinery. Power generation starts with a primary energy source, such as fossil fuels, nuclear energy, or renewable sources like solar, wind, and hydropower. These energy sources contain stored energy that can be converted into electricity. The energy source is then converted into a usable form of energy, often heat, which is used to create steam. The steam, under high pressure, drives turbines, which are large rotating machines with blades. As the steam pushes against the turbine blades, the turbine spins, converting the heat energy into mechanical energy. The rotating turbine is connected to a generator, which converts the mechanical energy into electrical energy. Generators consist of magnets and coils of wire, and as the turbine spins, the rotating magnets induce an electrical current in the coils, creating electricity. The generated electricity is then transmitted through power lines and distributed to homes, businesses, and industries. The renewable energy sources covered in this presentation are solar, wind, hydroelectric, and geothermal. Solar energy uses photovoltaic cells to directly convert sunlight into electricity, making it a clean and sustainable option for powering homes and businesses. Wind energy captures the kinetic energy of wind and converts it into electricity through wind turbines, often installed in wind farms with consistent wind speeds. Hydroelectric power plants use the force of flowing water to drive turbines and generate electricity, providing a significant amount of clean energy. Geothermal energy taps into the Earth's internal heat, using underground reservoirs of hot water or steam to generate electricity, particularly in areas with geothermal activity. These renewable energy sources offer a sustainable future by providing clean, reliable, and environmentally friendly ways to generate electricity. Advanced battery technologies like solid-state, lithium-sulfur, and flow batteries offer higher energy density, faster charging, and longer lifespans. These next-generation batteries are crucial for powering electric vehicles, storing renewable energy, and fueling portable electronics. Researchers are focused on overcoming technical challenges to make these battery innovations commercially viable and widely adopted.